My channel. Today let's see biochemistry class. So the first biochemistry class is on urea cycle pathway and its disorders. So let's go on. Urea cycle is also called as Krebs-Henselt cycle because Krebs-Henselt was the scientist who found out this urea cycle, and it is also called as ornithine cycle because ornithine is regenerated here, where I'll be mentioning in the flow chart. And it is also called as urea bicycle. Look at this picture. There are two cycles I have mentioned. First is TCA cycle and second is urea cycle. TCA cycle will give something to urea cycle, and in turn urea cycle will give something to TCA cycle. So what's that something? So TCA cycle will give aspartate to urea cycle, and urea cycle will give fumarate to TCA cycle. So TCA cycle is called as Krebs cycle. Urea cycle is called as Krebs-Henselt cycle. Therefore, it is also known as Krebs bicycle. This is the introduction. Coming on to the urea, we'll be seeing the structure. Its structure is NH2CONH2. There are two nitrogens. The two nitrogens comes from, one nitrogen comes from aspartate and other nitrogen comes from ammonia. And the carbon comes from the respiratory CO2. The compounds consumed in the urea cycle are aspartate, ammonia, and carbon dioxide. Where it happens? It happens in liver. Organelle is cytoplasm and mitochondria. Other cycles in both cytoplasm and mitochondria together takes place are, to remember this, I'll give you a clue, that is PUBG. P for pyrimidine synthesis, U for urea cycle, B for blood, heme blood. So heme synthesis, and G for gluconeogenesis. So coming on to the flow chart of urea cycle. First, as I said earlier, it takes place in mitochondria and cytoplasm. So first in mitochondria, there are two steps. First step is the carbon dioxide will combines with ammonia to form carbamyl phosphate. The enzyme used over here is carbamyl phosphate synthase 1. The short form is CPS1. Wherever synthetase come, you should add ATP. So in this step, two ATPs are utilized. 2 ATP is converted to 2 ADP. The allosteric activator in this step is N-acetyl glutamate. Without this NAG, this step won't takes place, and 2 high energy phosphate is required in this step. This carbamyl phosphate will combines with ornithine to form citrulline. This enzyme used over here is ornithine transcarbamylase, that is OTC. Fine, these are the two reactions taking place in mitochondria. Coming on to the cytoplasm, the citrulline formed in mitochondria is moving to cytoplasm, and citrulline combines with aspartate. Okay, where this aspartate comes from? This aspartate comes from mitochondria. It easily cannot transport from mitochondria to cytoplasm. It needs a transporter, that is aspartate glutamate transporter called as citrin. So aspartate enters into cytoplasm. So this citrulline combines with aspartate to form arginosuccinate. The enzyme used over here is arginosuccinate synthetase. As I said earlier, wherever synthetase comes, you should write ATP. There is a requirement of ATP. So 1 ATP is converted to 1 AMP. So this step yields 2 high energy phosphate. This arginosuccinate is converted to arginine in the presence of the enzyme arginosuccinate lyase enzyme, and fumarate is released over here and it goes to the TCA cycle. Arginine is converted to ornithine in the presence of an enzyme called as arginase enzyme, that is the class hydrolase class belong to. This urea is broken down. Urea comes out and regenerations of ornithine takes place. One more thing, the aspartate, where this aspartate comes to mitochondria, from where the aspartate is coming to mitochondria, this aspartate comes from Krebs cycle in mitochondria, which is happening in mitochondria, that is transported to the cytoplasm. And the ornithine is generated in cytoplasm, has to be transported to mitochondria, so it needs a transporter. That transporter is called as ornithine transporter, that carries ornithine from cytoplasm to mitochondria. This is a reaction of urea cycle. This is a pathway of urea cycle. Moving on to the next, I want to talk a little bit about the first enzyme, that is CPS1, that is a rate limiting enzyme. It is also called as pacemaker enzyme. Synthetase comes, so it requires 2 ATP, and most importantly it is a biotin independent carboxylation. The other examples of this biotin independent carboxylations are CPS2 gamma carboxylation malic enzyme. So totally 3 enzymes which are biotin independent carboxylation. And one more hint, in cytoplasm, all the enzymes will be starting with the letter A for the easy understanding. Coming on to the energetics. So in carbamyl phosphate synthase 1, we used 2 ATPs and 2 high energy phosphates. AS synthetase, in the sense arginosuccinate synthetase, it requires 1 ATP and 2 high energy phosphates. So adding up to all, it gives 3 ATP and 4 high energy phosphates. Coming on to the disorders of urea cycle. The first thing, um, carbon dioxide combines with ammonia to form carbamyl phosphate, which is CP. The enzyme used over here is CPS1. If the enzyme CPS1 is defect, it causes hyperammonemia type 1. And coming on to the next enzyme, that is ornithine transcarbamylase, where CP combines with ornithine to form citrulline. When OTC enzyme is defect, that is ornithine transcarbamylase enzyme is defect, it causes hyperammonemia type 2. Then comes the citrin combines with aspartate to form arginosuccinate. The enzyme used over there is arginosuccinate synthetase. When this enzyme is defect, it causes citrullinemia type 1. Arginosuccinate is converted to arginine in the presence of arginosuccinate lyase. If that enzyme is defect, it causes arginosuccinic aciduria. And coming on to the arginine, arginine is converted to ornithine. The enzyme used over here is arginase. If that enzyme is defect, it causes arginemia. So, and one more disorders in transporters. If the transporter citrin is defect, it causes citrullinemia type 2. Coming on to the ornithine transporter, if ornithine transporter is defect, it causes HHH syndrome, triple H syndrome. These are the disorders. Let's see the disorders one by one in detail. Coming on to the hyperammonemias. So hyperammonemias are type 1 and type 2. Uh, First, the enzyme defect in type 1 is CPS1 deficiency, that is carbamyl phosphate synthase enzyme 1 enzyme is deficiency. In this, what happens over here is when ammonia levels is increased, do you think which amino acid will be detoxifying it? It is glutamate. The transport form of glutamate ammonia is glutamine. So there will be increased glutamine in type 1 hyperammonemia. Type 2 is OTC deficiency, that is ornithine transcarbamylase enzyme is deficiency, and there will be increase in glutamine. When compared to type 1 and type 2, type 1 has the increased levels of glutamine in the plasma compared to type 2. Talking little bit about type 2 hyperammonemia, look at the picture over here. This carbon dioxide combines with ammonia to form carbamyl phosphate. The enzyme defect over here is ornithine transcarbamylase is defect. So the carbamyl phosphate cannot combine with ornithine to form citrulline. So what happens is this carbamyl phosphate will move to the cytoplasm from mitochondria. Got it? So this carbamyl phosphate enters a new pathway called as pyrimidine synthesis. And there what happens, it forms a oratate. From there it produces uracil and it gives cytosine and thymine. When orate is accumulated, that is the intermediate product in pyrimidine synthesis. When orate increases, it causes orotic aciduria and it causes accumulations of orotate crystals, and pink granules will be appeared in urine, and this is insoluble in water. So the distinguishing factors of hyperammonemia type 2 are orotic aciduria. There will be increased in pyrimidine synthesis because cytosine and thymine, uracil all are pyrimidines. Purines and pyrimidines, especially the pure pyrimidines, are increased in this type 2, and it is X-linked, partially dominant, and it is partially recessive. And the most common urea cycle disorder is type 2 hyperammonemia, which is 40%. Next, coming on to trichohexis nodosa, it is seen in the deficiencies of arginosuccinate aciduria. Okay, so trichohexis nodosa, it is seen in arginosuccinate lyase enzyme is deficiency, and the disorder is called as arginosuccinic aciduria. We can see this in the newborn. The hair will be so brittle, so soft, and there will be nodes in the hair, which you can see in the left hand side picture. That is called as trichohexis nodosa. Coming on to the HHH syndrome, triple H syndrome. Um, as you all know, the defect is ornithine transporter. The transport is defect, so ornithine cannot be transported from cytoplasm to mitochondria. So this mitochondria, mm, in cytoplasm this ornithine gets accumulate. Okay, and in mitochondria it cannot be combining with carbamyl phosphate. So what this carbamyl phosphate will do, this carbamyl phosphate will be combining with lysine, and it forms homocystinuria. That is, you can see 1H for homocystinuria. There will be hyperammonemia, as I said in the beginning. So urea cycle is always associated with increased in ammonia levels, and hyperornithemia, that is because this carbamyl phosphate will cannot be combining with the ornithine, so ornithine level will be increased in cytoplasm. That is a cause for hyperornithemia. Homocystinuria is all because of this carbamyl phosphate will be combining with lysine to form homocystinuria. That is called as triple H syndrome. Coming on to the arginemia, it is the least hyperammonemia. Why? Because the nitrogen is already ejected. Arginase enzyme is isoform, and it is active to progressive spastic dysplasia, that is the seizing of lower extremities. Coming on to the common clinical features, there will be encephalopathy. I'll explain this encephalopathy. In general urea cycle there will be increased in ammonia level, that causes depletion of alpha ketoglutarate, that in turn decreases the ATP, in turn causes the glutamate level increases, and glutamate is converted to glutamine because transport form of ammonia is glutamine, and that glutamine causes a cerebral edema. This glutamate will be increased, that causes the increase in GABA, which is the neurotransmitter which causes CNS depression, that is behind encephalopathy. And there will be hyperammonemia, as I said, and there will be respiratory alkalosis, that is hyperventilation. That's why in especially in neonates, there will be feeding difficulties, there will be lethargic, and if untreated the babies will go to deep coma. These are some of the clinical features of urea cycle. Coming on to the investigation, first we'll be seeing for looking for the plasma ammonia. This is tested by two methods. One is by ammonia selective electrodes, and next is enzymatic method, that is glutamate dehydrogenase enzymatic method. And we'll then look for the pH and plasma bicarbonate. When the pH is low, we'll call as acidosis. When the pH is high, we'll call as alkalosis. When pH is low, we will be suspecting that as organic aciduria. When pH is high, it leads to disorder, that is urea cycle disorder. One specific amino acid elevation will be there. If that amino acid elevation is present, then when there is increased in citrullinemia, that is citrulline that causes citrullinemia. When there is increased in arsenic succinate, that causes the arginosuccinate aciduria. When there is increase in arginine, then it causes the arginemia. When there is increase in ornithine, it causes triple H syndrome. When this specific amino acid elevations is not there, when it is absent, then we'll be looking out for the plasma orotic acid. When the plasma orotic acid is present, it is hyperammonemia type 2. When plasma orotic acid is not present, then it is hyperammonemia type 1 disorder. These are the investigations of urea cycle disorder. Coming on to the treatment, first line of treatment. First line of treatment is arginine. Why? Why we are giving arginine? Okay, I'll explain. It provides ornithine, a positive regulators of urea cycle. Why? Because ornithine will combines with carbonyl phosphate to form citrin, citrulline, and it goes off in a cycle. And we'll be providing the allosteric activator, which is NAG. The enzyme used over here is NAG synthase, where it increases the NAG, that is N-acetyl glutamate. It is a positive regulator for urea cycle. I'll just say the formation of NAG. Acetyl CoA will be combining with glutamate to form NAG. The enzyme used over here is NAG synthase. So, allosteric activators of NAG synthase will increase the NAG, a positive regulators of urea cycle. And administrations of essential amino acid, which are need for neonates. And the contraindications of this treatment is arginase defect disorders are common. Coming on to the second line of treatment. Second line of treatment over here will be acylation therapy. What is this acylation therapy? Administrations of sodium benzoate or phenylbutyrate is used. What is it, sodium benzoate and phenylbutyrate? It is sodium salts of organic acids. Okay, let's see the mechanism of action. The phenylbutyrate is metabolized, and this phenylbutyrate is prodrug. This phenylbutyrate is metabolized to form phenyl acetate. This phenyl acetate will combine with glutamine. Where this glutamine comes from? It comes from ammonia. combines to form phenylacetylglutamine, which will be excreted in the urine. This is a mechanism of action of phenylbutyrate. Coming on to the sodium benzoate. This sodium benzoate combines with glycine. Where this glycine comes from? Ammonia. And glycine is a non-essential amino acid, which you all know. So it combines to form benzoyl glycine, which is called as hippuric acid. This hippuric acid will be excreted in the urine. This is a treatment of urea cycle disorders. And very simple topic, urea cycle disorder, which comes under protein metabolism in biochemistry. All the very best. Thank you.